Yeah, so let's get started. Mm, I think a few people will join, but it's already 6:05 in my watch. So let's wait for a couple of seconds, maybe minutes, then we'll start. Because I mean, this is like continuation of our previous this thing. You know, one second. Yeah, so it is like continuation of our previous classes only. I mean, last class. So here the thing is, we play around mostly with this concept of effective interest rate in the case of compounding, uh, like that. In the previous class, we usually did not consider this parameter. We just took the interest rate that was given as this thing, um, annually compounded annually interest rate. But that is not always that that must not be always true. It can be compounded quarterly, daily, or continuously also. So continuously is more or less like a theoretical uh, thing. It's not a, I mean, it's not like that. So like many practical applications will not have continuous compounding. So continuous means it is like you do compounding at you know, very large number of times. Uh, Typically, they call it as n tending to infinity. All those things. Okay, so um, that's like a theoretical case. Uh, so we'll see those things, and what we did in the last class. Those two cases of single payment uh, factors. Then there were uh, four cases of equal payment series. Okay, and then there was these two geometric series, right? One was uniform and another one was, I think, geometric. Okay, so in those cases, whatever I or rate of interest symbol that we used, variable was I. So effectively, that is, uh, we assume that it is a uh, annual compounding interest rate. But as I said, it can be weekly or any time frame within a year. So in that case, uh, in all of the previous formulas, you just need to replace I. Okay, so all those formulas are still valid. It's just that the I value, which was assumed to be, uh, this thing compounded annually, now it will be compounded with some other time period, but you can convert it into an uh, annual effective interest rate compounded annually, and then you can use the same formulas that we had previously. Okay, so it's uh, it's more or less the same thing. It's just that in this like week 4 classes, additional things were there for this continuous compounding case. So all the formulas uh, were just repeated. So okay, what I mean by that is I'll just tell you once we start the class. Okay, and then you know uh, uh, that is like broadly the topics that were covered, and then there was some discussion on equivalence. But we talked about equivalence in a sense in the previous class only, because that time we discussed when we were solving the last problem of deferred annuities. So basically, you want payment after your retirement, right? Let's say normally we call them as pension, not annuities. But for that you save from your professional career only, right? So basically, you save from now, and at the end of your professional career, there will be certain lump sum amount in your pension account, and then you expect some fixed pension monthly pension amount to be credited to your bank account for next certain number of years, right? So we solved one problem towards the end of the class, that let's say if I retire after 25 years from now, I want pension for next 25 years or something like that. So how much should I put in as a bulk today, or you can do monthly also. You can calculate how much monthly contributions towards this NPS or PPF that you should do, so that after your retirement you will get certain pension, right? So that is nothing but the way we solved that problem was we first calculated the present value of your investment at the end of your, like we assume that you reached your retirement day, and then how much you need to put in your retirement account so that you get annuity of certain amount compounded with certain interest rate. Okay, so then we discounted that value back to the current future. Okay, so same thing, if you understood that concept, this equivalence is more or less based on that concept only. It says that you cannot they talk about cash flows, etc., but basically you cannot compare one amount at particular time, t equal to, let's say, t1, and another amount which is to be deposited or whatever it is at some other time, t2. So you need to convert them to one time, and then only you can do the valid comparison, which makes sense, right? I mean, it's like a practical thing only. You, let's say you have 10,000 today, and you are saying with certain interest, etc., I want 5 lakhs later on. Okay, so if I ask you which quantity or which is the better option for you, you can't just compare it like that, right? So there are two ways to do it. Either you take this 10,000 and whatever interest you are getting, let's say you're doing FD or something, you calculate your future value, assuming the compounding or whatever simple interest, whatever that you get from the bank. And then you can compare your final values, right? That after certain number of years, whatever amount you have, that is one way. Another way is you discount that future value, which you expect at the end of certain time period, to the present value. Okay, so then only you can compare the two numbers. Otherwise, comparing two different amounts, which are at two different time in the calculations, it's invalid comparison. It's wrong. It's invalid actually. You cannot do that. It's obviously wrong, but it's not allowed also, and you should not do that. So you should always try to convert everything to a certain time period. Okay, and some problems were also discussed in the class by professor. You should look it up. Okay, because so far we have discussed many things, and it's basically application of all those things. Okay, so and then this this is about the equivalence. So basically equivalence is like you have to convert every quantity at a particular time and then do the comparison. And then there are some things like outflow is equal to inflow. So basically conservation of see, if you are from technical background, there is something called as conservation of mass, which are like basic identities of any system. So whatever comes in, whatever goes out, in steady state, they have to be equal. Otherwise, there will be some accumulation or rejection from the system. So basically, that concept is followed in some sense for the inflow, or call it as receipts and disbursements. Okay, so those things were also discussed towards the, I think, last class of week 4 before the problem solving session. So those things are there. So we'll briefly recap everything, and then we'll start solving some problems. Okay. So yeah. So in this class, the first thing is about that effective. In some places, you'll find this term which is called as EAR. Okay. So that is nothing but abbreviation for effective annual rate, and basically what professor also denoted as effective interest rate per annum, compounded annually. Any term you can use. We'll use this acronym, which is EAR, effective annual rate. Okay, but you should understand what I mean by this. So basically, by doing this, you are making your life easier. Why? Because let them do compounding for any time interval. You convert that into EAR, and then use the formulas that we discussed in the previous class. we had some 2 plus 4 plus 2, right? So around 8 formulas were there. And uh, so if you understood that part, here you have to just convert that current interest rate into annual effective EAR, or an effective annual rate. Okay, how do you do that? So for a particular like normal case, basically I is you know this EAR is nothing but uh, this thing, right? How should I say? Okay, I'll use this abbreviation EAR. It will be nothing but the thing is, it is nothing but your future value minus your principal. Okay, so we have this divided by your principal. Okay, so this is a basic formula. One second. Excuse me. Or otherwise, you know, so in some cases, one second. So in some cases, they also call this as interest that you get, or returns that you get on your investment divided by the principal, that is the principal that you invest today, or t equal to 0. Okay, and we know that f is nothing but p into 1 plus r power n. Okay, this we saw previously, right? But this is valid if this r is nothing but this is valid for if r is uh, interest rate compounded annually, right? Okay, so this is what we saw in our previous class. So all the cases were uh, more or less assuming this. Okay, so now the thing is, it is not necessary to have R which is compounded annually. Depending on the case that you you know encounter, it can be any other time period. Okay, so that is what is the new change here, and it is basically 1 plus R by, let's say, M, and then M into N. Okay, so the difference here is uh, R is interest rate compounded with the frequency of M per year, or annually, you can also say like that. So basically, when I say compounded quarterly, so there are 4 quarters, right, in a year. So that means M is 4. Semi-annually, uh, that means you semi-annually, because these are some keywords which are commonly used. This implies M will be 2. Okay, quarterly, again very commonly used term. Quarterly implies M equal to 4. Then you'll have something called as daily, where we typically take M, or before daily we should do weekly. So weekly would be usually 52 weeks are there, and if somebody mentions that it is interest rate is compounded daily, that means M is nothing but 350. Oh, sorry, 365. Okay? Because there are usually 365 days in a year. If they have specifically mentioned that it's a leap year, then you should take 366. But 365 is generally uh, commonly used. And sometimes they use this term which is called as continuous compounding. So it's a theoretical case. So that means this M tends to infinity. Okay, so basically it's a very small time period for which you are holding the money, and then again very quickly you are compounding. This is more or less theoretical case, but you know, I mean, you should know. Okay, so this is how this M comes into the picture as to our previous cases. And then, this EAR, EAR is nothing but FP minus 1, right? I mean, this formula itself, you can see the F minus P by P. So if you do this, it is nothing but 1 plus R by M, Mn minus 1. Okay, so this formula is coming from that side. And then, uh, in the case of this continuous, in case of continuous compounding, which implies that M tends to infinity. In that case, your EAR, let's use the subscript infinity for continuous compounding. It's nothing but limit M tending to infinity 1 plus R by M, Mn minus 1. So here R and N are constant. The only variable is M. Okay, so you can do this thing also. I hope you know how to calculate limits. If not, I'll just tell you. It's not that difficult. Basically, put R by M as, let's say, some variable x. Okay, and then as M tends to 0 or infinity, your n x tends to 0, right? Because it is R by M. So your limit shifts in terms of variable x. So when x tends to 0, this is 1 plus R by M is x, and then you have Mn, right? So this Mn, you can write this as M by R into NR, right? Why am I doing it? Because this M by R I can write 1 by x into this NR. This remains as it is, minus 1 remains as it is. And it is a property of limit. Since n and r are constant, I can take it inside a bracket. So extending to 0, 1 plus x power 1 by x whole raised to nr power, and this minus 1 is a constant, so it remains as it is. So this is nothing but it's a standard result. It's nothing but this 1 power infinity, right? So you have to take log on both sides, and if you solve for it, you will get this e power nr minus 1. Okay. So this is a classic example or result. Okay. So yeah, this is the special formula for your continuous compounding effective annual rate. Okay. So since this is a new case, that's why we are discussing it. I think you will have some problems in your assignment also based on this. Okay. And one more thing they usually ask is what is the future value if you do continuous compounding for some time period. Okay, so in that case, you should know that this f is nothing but p into this rate limit m tending to infinity 1 plus r by m power mn minus 1, right? This is your f, if I'm not wrong. Yeah, and since we calculated this, it's basically I'll put f subscript this so that you understand this is a future value when you are doing continuous compounding. So in that case, it will be nothing but p into e to the power nr minus 1. And if in some question, if they ask you not the future value, or they ask you interest. Okay, so for example, if you are doing some continuous compounding, how much is the interest that you accumulate after 1 year? So in that case, this I infinity is nothing but the interest accumulated during compounding, continuous compounding. That is nothing but f infinity minus p. That will be nothing but p into e to the power nr. Okay, so that one goes away basically. So these kind of simple things can be asked. Okay, so I just thought I'll give you everything in one place. Okay, so that is one thing. You can do this derivation in another way also. You know, I mean, starting from this f also you can do, but in the end you have to take the limit somewhere, and you'll get this form where you have uh, you know 1 plus x power 1 by x when x tending to 0. That is e, and e is a constant. Okay, so it's a irrational number. I think we discussed this 2.7182 blah blah blah. But for all practical purposes, every calculator has usually that e variable directly, or otherwise you have to take 2.718. Okay, at least maintain accuracy up to 3 digits after decimal point. Okay, and then this was the major thing. Then what is happening is this thing, right? All the previous cases, mm, previous cases, and by that I mean discussed in the last class, right? Discussed in the last class can be extended to special case of continuous compounding. So you know for that matter, yeah, I should first write non-annual compounding, okay, and then the special case of continuous compounding can be extended to non-annual compounding, and then to the special case of continuous compounding. Okay, so what I mean by that is, as I said in the last class, we all assumed, in all cases, we assumed that it's a interest rate compounded annually. Not necessarily, right? So, what does that mean? That means, this uh, first thing, we had two cases of single payment, right? So, let me just go back to those notes. Yeah. So, what I mean by this is, you can use still the same formulas that you had. It's just that this I will change. And what I mean by that is, let's say this first, this single payment factors were there, right? Two cases were there, right? One case was this compound amount factor, right? So here, if you remember, we had done, f equal to p into 1 plus I power n in the last class, right? But the thing is here now, whatever the problem that you have, you need to first calculate EAR, or effective annual rate, and then you need to put that in this bracket. So here it will be EAR power n, or in our other notation it will be, if you have interest table etc with you, it will be f by b comma EAR comma n. Okay, so the formulas remain same, only in place of I you have to put ER. Okay, and then there was a second case where you had a present worth factor, right? So there it was, p equal to f into 1 plus I power minus n, correct? Now that I will be replaced by EAR, because in the problem you will not be given interest rate compounded annually. They will give you some another frequency, and then you just have to first calculate ER for that case, and then put it. And the same thing if you have interest tables or interest factor tables, you have to put EAR and N, and then get that factor from the table. Okay, so like this, everywhere you have to do this only. Okay, I hope you understand what we are doing. Okay. Then there were four cases of equal payment series, right? So there also replace I by this EAR value. Okay, this is assuming that we are not doing uh, this thing, continuous compounding. Okay, and like not only for that equal payment series, even you have that gradient, etc., right? So in those cases also, you have to replace I by EAR. Okay. Four cases of equal payment series and two cases of gradient series. Okay, so this is applied to the previous class things. Now the special case of this thing, special case of continuous compounding. So in this case, the formulas slightly differ because now you replace this I in our previous formula by this EPF EAR infinity, right? EAR infinity is this e power n minus e power nr minus 1. Okay, so you have to put that everywhere. So if you do that, you know this special case of what is it? Continuous compounding. Okay, so here basically your EAR, we are using infinity as a subscript, is nothing but NR minus 1. Okay, N is the number of years, R is the interest rate compounded with certain frequency. Okay, so based on that you get EAR infinity, and then you have to put that in the formula, but then your formulas will change, right? Because for example, if in the derivation, let's take um, one second. Mm, okay, let's take the simple one, which is compound amount factor. So it was F and A, right? The compound amount factor is the relationship between F and A. So um, let me just see if I made any mistake previously. One second. Yeah, RN, right? Yeah. Then that will, yeah, this continuous case. Oh, e power R minus 1. Yeah, yeah, there is some mistake here. One second. Mm, what is the mistake? 1 by R is 1 by X and R, right? Mm, See, since this is annual rate, right? Yeah, the mistake is here. See, this F formula, these are for any number of years. But when you talk about EAR, basically it implies that, you have to take it for n equal to 1, right? Then only it will be annual, no? So that's why this n doesn't come into picture anywhere. Yeah, yeah. Okay. Yeah, so that is the uh, one thing that I missed. No worries, nothing is wrong. Nothing is wrong per se. But the only thing is, since we are here, n will come because we are doing f infinity, right? So here it should be fine. E to the power nr. Yeah, this is fine. In the EAR, there is no n. Yeah, that is the difference. Then it makes all the sense, because otherwise, those formulas were different than what you should supposed to get. Okay. So, in this case, what you have to do is, this uh, the formulas are different here because of this special case. Okay. What I mean by that is, you can take this single payment uh, cases. Okay. So there are two cases, right, in single payment. Okay. First is compound amount factor. Let's say I'll call it as CAF, because we have already written all these things here. Okay. So here, the formula is nothing but F equal to P1 plus EAR infinity power n, right? So then you have to put e power r minus 1 in this place. So you'll get F equal to P into e to the power nr, right? Because r and n will get multiplied. So basically, you can write this again as, if you have this table for this given r, you can write it as f by p, comma, this will be your r comma n, right? Because for given r and n, uh, you have this. Okay. Yeah, since you are taking that e already into account, you can just write it in terms of r and n. No need to write it as EAR infinity here. Okay, so don't commit that mistake. And then there was this present worth factor, right? PWF. This PWF, and it will be nothing but P equal to F into 1 plus EAR infinity power minus n. So therefore P will be F into e power minus nr. Okay, you can write this as F into P by F r comma n. Okay, since this e is already there. Okay, so this is how you should go about it, because sometimes what will happen, this EAR infinity will not be a standard number. Okay, it will be not like 1%, 2%, 10%, like that. So in that case, you should be able to use the formula directly. So that's why I am writing this again and again. So I'll not write this part going forward. I'll just give you the formula, or maybe I'll write it, but I mean, you understand, right, what is the significance. So this EPS, equal payment series, there were 4 cases, right? Let's say the first one is again compound amount factor, the CAF. So here you'll have F equal to A into I plus, this formula was there, right? 1 plus I power n minus 1 by I, right? So here put I equal to EAR infinity, which is nothing but e to the power r minus 1. Okay. So if you do that, what you'll get is, if F is equal to A, and you know this plus minus 1 will get cancelled. This will be nr or rn minus 1 by I is e power r minus 1. Okay. And this again you can call it as, if you have this data in your data book or in your questions, then you can use it, but the formula is as follows. Okay. Similarly, you have to do this for other three cases in EPS series. Okay. So, you know, uh, what were the three cases? I'm just writing it for the sake of completeness. Okay. So this, present work factor, then that will be, between A and F, right? One second. Uh, no, no. See, A and F is capital recovery. Compound amount factor is F and A. Sinking fund factor is the ulta one. Yeah. Sinking fund factor. Okay. So here also you have to replace I from last class formula with e to the power r minus 1. Okay. If you do that, you should get A equal to F into this ulta of this e power r minus 1, e power n r minus 1. Okay, and they sometimes write it as F into A by F for given r and n. Okay, so like that you'll have two more cases. Okay, so EPS. So what are the remaining two cases? Sinking fund is done, compound is done. Yeah, then there are this capital recovery factor, right? Okay, so here basically um, one second. Yeah, it is between A and P. Okay, so same thing, you have to do replace I with e power r minus 1, and if you do that, uh, you should get A equal to P. There is one term I plus n power n, 1 plus I power n, so that will become e power n r, and in bracket you will have I, so that will be e power r minus 1 divided by 1 plus I power n, so that will be e power r n minus 1. Okay, so you can just divide this by e power nr, and then you'll get 1 minus rn. Okay. And now this factor becomes your um, capital recovery factor. So that is how it goes. Okay. And then the last case would be capital recovery, then present worth factor. Okay. So this will be between P and A, right? So in that case, it will be P equal to A, ulta of this. So minus Rn e power r minus 1. And then you can write this as A into P by A, comma r, comma n. Okay. So, and then, this geometric series also you can do. So there also you have to replace I by, uh, you know, this thing. Um, what do you say? Uh, in geometric series, we had two cases, right? There also replace I by e to the power r minus 1 for continuous compounding. Okay, this is like a note, because I don't want to give you the formula, because the thing is, again, those formulas are difficult to remember, because in uniform geometric payment in uniform gradient payment series it's still okay. And I think the professor had given you formula in the class itself for that. But for geometric and all, since there are three sub cases already there, so it's also same thing, only in that G dash formula you have, right? G dash equal to 1 plus I by 1 plus G minus 1. So there you have to put I as e power n minus 1, e power r minus 1. So it just becomes e power r divided by 1 plus G minus 1. Okay, so like that. Okay, I can just give you also, since we are there. So uniform GPS case. So if you replace I by e power r minus 1, you will have a equal to G into 1 by e power r minus 1 minus, this will be n divided by 1 plus I power n minus 1, right? So that is e power rn minus 1. That's it. It is like this only. You have to replace I by e power r minus 1. Okay, and that geometric series was there, right? Geometric GPS. So there, if you replace, this G dash was 1 plus I divided by 1 plus G minus 1, right? So here, if you replace I by e power r minus 1, so this just becomes e power r 1 plus G minus 1. Okay, and then this is your G dash. So there are three sub cases for G dash, right? So those remain same only. So there is no change there, because G is not a function of I. It's a separate parameter, right? So only I is replaced by e power r minus 1. Okay. So this was the whole summary of the formula that are added because of continuous compounding. Okay. Um, but if you have understood the basics, it will be easy only. It should be fine. And then there are some things like if you don't have same interest rate throughout your period, what to do and all. So it is it is it is like a basic idea, right? So let's say you are doing some FD, and for 2 years you get some interest at R, or let's say 5%, and for third and fourth year you get 6%. Okay, so in that case you can't just calculate the fourth year amount, right? For future value after 4 years based on any common or any single interest rate, right? So you have to first calculate the future value based on first 2 years of interest rate, and then you need to calculate the last or the final future value based on the taking the future value after 2 years as the present value, and then compounding it for next 2 years. So like that. So that is how you tackle different interest rate cases. And then there was something, one sample problem was also discussed by the professor, where you basically, as I said in the beginning of the class, it's like that same problem, right? That annuity, deferred annuity case, right? So you basically go to that place where you are doing your annuity start, calculate the future value, and then discount that future value to the present. Okay, so we had done one last problem in the last discussion. If you are confused, you can go back and check that. Okay, so we basically do that only. Okay. So with that, let's discuss some problems, because enough of theory. But if you remember this way, I think it will be easier for you to remember these formulas for your exam, if you are planning for it. Okay. So let's go and solve some problems. So let's first solve this, effective interest rate and all those things. Okay. Yeah. So this kind of problems are also asked in many competitive exams also. So the rate of interest, compounded quarterly, to make an investment double in 5 years will be, in percentage you have to answer. Okay, so here basically this is a classic problem. You can have many variations of this. So here basically, let's say you have certain present value P, and what they're asking is your future value should be twice of your present value after number of years, 5. Okay, at what are compounded quarterly? So this is the question, right? And since it's a quarterly compounding, it means m equal to 4 in our effective interest formula. Okay, so we know this is not a case of continuous compounding, so just this 1 plus r by m n. Okay. So here f is 2p, so pp gets cancelled. This is 1 plus r by 4, and m is 4, n is 5, so this is 20. So therefore it is nothing but r by 4 equal to 2 to the power 1 by 20. Okay, now for this you have to use calculator, or otherwise you can take log on both sides also. This is also one way to solve. It will be nothing but ln 1 plus r by 4 equal to this 1 by 20 into ln 2. Okay. Anyway, whichever calculator you have with you, but it is easier to remember ln 2 because it is standard value. I think it is 0.693 if I am not wrong. Let me just confirm. Yeah, 0.693. If you divide it by 20, that is 0.0346. Then you have to do the exponential of this, right? 0.693. Sorry. Yeah, e to the power 0.693 by 20. One second, I'll use my calculator in my mobile because this PC calculator is bad. So e to the power ln2. Be careful about this ln and log. Okay, so this is a natural log, not a logarithmic like 10 base. It's not 10 base, it's a natural. And then you need to subtract 1 from it, right? Minus 1 and into 4. So you should get 0.14. If you solve any of this, you should get 0.141. Okay, so that nothing but it means r equal to 14.1%. This is your answer. And if I, like what I said, is this is a classic example, right? It can be modified easily. So instead of asking it to be doubled in 5 years, I will say what if it has to be triple in 6 years. Okay, so like that you have to change the value of n, and f equal to 3 we have to put. if I ask you, instead of compounding quarterly, if it is compounded daily or semi-annually or weekly, then accordingly you change your M value. Okay. So I'm not doing that, but I'm just giving you that many a times you can do this way also. I mean, you can expect such problems in your assignments as well as your exam also. Okay. So let's take next question. So they are asking about effective annual rate for nominal interest rate 12.75% compounded semi annually. Okay, so this is also again one of the classic problems. So since they have given you a nominal interest rate, so that is nothing but R, so that is 0.1275, and they are calculating it semi-annual basis, so M will be 2 here, and what they are asking is what is EAR for this condition. So you just have to use the standard formula for EAR, is nothing but 1 plus R by M. Here you have to put n equal to 1 since they are asking about annual case. So let me just check what did I give you initially also. Yeah, here also I mean n has to be 1, so okay. Yeah. So in this case it is nothing but 1 plus 0.1275 divided by 2 into raised to 2. So if you do this you should get the answer as 0.1314. Okay, so that is nothing but 13.14%. Okay. So like this you have to calculate. So I can give you another formula where I will change R, I will make it let's say 10%, and I will say compound it this thing daily or something like that. Okay. So in that case you'll get different answer, but the formula is same. Okay, so like that also you can do. Okay. So then this another sample problem for continuous compounding case that you can expect. So the question is, what nominal interest rate value will result in a 14% effective annual rate for continuous compounding. Okay, so in this problem they have given you the EAR for for continuous compounding as 14%, right? So you can write it as 0.14. Right, and what they are asking is what is the value of R. Okay, so here you should notice one thing, that they have not given you any M and all those things, because it's theoretical condition or limiting case where M tends to infinity. Okay, so here basically you have the formula of EAR for continuous compounding as e power R minus 1. So basically they are asking what is the value of R for this relation. So this will be 1.14, and then you have to take ln on both sides. So R will be nothing but ln of 1.14, and since it's greater than 1, the value will also be greater than 1, less than 1. I mean, since it's less than E, the value of ln will be less than 1. So that will be 0.1310. and that means your uh, nominal rate must be this much, so that you'll get 14% of effective annual rate compounded continuously. I can frame the question in another way also, where I will give you R, I will ask you EAR infinity. Okay, so we are not doing it, but I hope you understand what all can be asked. Okay, accordingly you should be prepared, or expect such things, because these are like standard template problems, and can be asked. Okay, then okay, so yeah, we can take one more problem, another variation of this compounding, etc. Okay. Okay, so and or the amount of 5 lakhs borrowed today at interest rate of 16% compounded quarterly has to be returned after 3 years. The amount, or I would ask the total interest paid will be. So slight one step ahead. In the original question, they were just asking what is the total amount that is returned, but I am asking interest. Nothing difficult. Just giving you the whole this thing. So here you have a present value of 5 lakhs. So 5 into 10 to the power 5. R is given as 16%, so 0.16, and they're compounding it quarterly, so M is 4, right? And N is 3 because 3 number of years they are asking. Okay. So here F is nothing but P into 1 plus R by M power Nm. Or otherwise, if you have table for 14 or 16%, you can write this as F by P R comma N, which is nothing but uh, yeah, see this R and N, these are for annual things, right? So here R will become R by M and N will become Mn. Okay, so keep that in mind. So nothing but F will be 5 into 10 to the power 5 into 1 plus R by M will be 0.04. 16 by 4 is 4, and this will be 12. 4 into 3, and this is also, if you have the access to these tables, it will be F by P. R by M is 0.04, Mn is 12. Okay, so whichever way you want to do. So F will be nothing but 1.04 power 12 and into 5 lakhs. So that is around 1.6 times. So you should get around 8005000, and therefore interest will be nothing but future value minus present value that you pay for. So that will be 8 lakh minus 5 lakh, so right, 3 lakh 500. Something like this. Okay. So like that, there are different problems. Then Let's see one more problem we can do. Hmm. One second. Hmm. Okay. Yeah. So this is the question. Slightly confusing language, but not that difficult. Okay. So the question is: a man decides to make semi-annual payments, or I should just say, a man makes semi-annual payments of 1,000 rupees each into a bank account that pays nominal interest of 6% compounded weekly. Okay, the total amount accumulated uh, in the bank in his account at the end of 10 years will be how much? So this is the question. So now they are trying to confuse with the language. That is the problem. So don't worry. In such cases, you should always take the n. Usually we take n. I mean, um, you know, n as number of years, right? But here he is doing the payments on semi-annual basis. Okay, so he's not doing them on annual basis. So that is first difference. And these are equal payments. So each payment will accrue some interest going forward, and till 10 years. Okay, so I can I don't want this confusion of years and semi-annual year, right? So what I will do, I will ask him, I will solve this question by assuming 20 semi-annual years, right? So what I mean by that is, this 10 years is equal to 20 semi-annual payments, right? So that is first thing. So therefore, for this problem, it is better to solve this by taking n equal to or this m equal to 20, right? No, sorry, m is different thing. This 10 years, take it as 20 semi-annual payments. That is first case, so that you will not get confused. So now everything you are doing, you are just focusing on 6 months of the year. Okay. So here, one thing is, again, one additional this thing is they are compounding the interest weekly. Okay, so let's convert that into effective interest for 6 months, right? So effective annual rate. Actually, we should not call this annual because this is not annual. So effective interest rate for, let's say, 6 months, because we are now looking at semi-annual payments, right? So here, um, it will be 1 plus r by m power mn minus 1, right? So r is given as how much? 6%. So 0.06. M is nothing but the frequency. So they are compounding it weekly, and in 1 year there are 52 weeks. But in M is 52 because this M comes with the interest rate only. So R by M, that is fine. This N will be 1 by 2 because uh, you know this is for 6 months. So because of this semi-annual thing, it will come like this. Okay. So if you plug these values, you will get R by M will be 0.06 by 52, and this 52 into 1 by 2 will be 26 minus 1. Okay, so that should come about 3.044%. Okay, you can verify this. Let me just do it only. I don't want to commit any mistakes. Okay. 1 plus 0.06 divided by 52 raised to 26 minus 1. Yeah, you find, yeah, this is correct. And now, see, now this is the case of our regular problem, right? Where uh, you are doing the semi-annual payment for 20 times, and then you need to find the final this thing, right? What do you say? Future value. So now we need to use this formula, right? F equal to A, because these are equal annuity payments, right? 20 installments, right? And then it will be 1 plus this effective rate. So let's say we call this as some R dash. Okay, so this will be R dash power 20 minus 1 by R, or R dash here. Okay, or if you have tables, but then you have to access the table for 3%, right? So here you will have F by A comma R dash comma 20. Okay, so like that you need to, and this is your R dash essentially, uh, because I'm not calling it R because it's not annual. Okay, it's a semi-annual basis because the payments are being done semi-annually. So instead of 10 years, we are solving it for 20 semi-annual payments. So if you do that, this payments, this A is nothing but 1,000 rupees because he is doing semi-annually payment of 1,000. This will be 1.003, right? So 03 only, 10 will come. 3044 power 20 minus 1 divided by 0.03044. Okay, so you have to calculate this. Let me just do that. 1000 into 1.03044 raised to 20 minus 1, 0.03044. Yeah. So at the end of 10 years or 20 semi-annual payments, you would have 26,990.9. Okay, so let's say, I mean, you can round it off to 26,991 also, but you should get answer somewhere close to this. Okay. So does it make any sense? See, he is doing 1,000 per 6 months. So in a year, he is approximately doing 2,000. In 10 years, it will be approximately 20. Yeah, so your final answer should be greater than 20. That is first sanity check. And it makes sense, right? Because, this interest rate is like 6% compounded weekly. So, uh, yeah, I mean, on a 6 months basis, it is 3%. So, yeah, I think that should be fine. So, like this, you have to solve such problems. Okay. So, let's take one more question like this. Uh, mm, yeah, one second. Okay, so now, yeah, let's take this question. So basically, uh, in this question, what they're saying is, for purchasing an equipment costing 40,000, let's say for purchase of worth 40,000, down payment of 10,000 is made. Down payment of 10,000 is made, and uh, the remainder is borrowed from the bank at 9.6% interest, compounded monthly. Okay. The loan is paid in 40 equal installment. 40 equal installments, and the amount of monthly installment you need to find. The amount of monthly installment will be, that is the question. So now, see, first of all, this P will be 40,000 minus 10,000, right? Because you did the down payment then initially only, right? So P is nothing but 30,000. So you need to pay this with 40 equal 40 equal installments at 9.6% compounded monthly. So basically, they are asking what is your A value or annuity value. Okay. So here the easy is because R is also given compounding monthly, and 40 are monthly payments only. Okay, so everything is in months. Okay. Okay. So and here n is 40 months. So let's say we are talking about 40 as n value. Okay, and we need to find A, but for that first we need to find the effective interest rate per month, right? Because see, they are mentioned that it is compounded monthly, but it's not the monthly rate, right? So this 9.6 is a okay, it is 0.096 divided by 12. Okay, so that will be 0.08%. Oh, not percent. So 0.08 per month, or 8% per month. Okay, so this is per month. So pay attention to this, because usually you will see 9.6% compounded monthly, but that is not monthly rate. That is like compounded monthly. Okay, so like that you have to pay attention to these things. And then uh, this is N is also 40 months. So you need to find A from P. Okay, so that is nothing but you need to, if you have the access to uh, tables, you need to do it this way. Okay. Or this formula, we had this formula, right? Since these are equal payments, you have to use this capital recovery factor, you know. So that will be nothing but 1 plus I power n into I. Okay, so it is nothing but, let's say I call this as r dash. So it will be 1 plus r dash power n into r dash divided by 1 plus r dash power n minus 1. Okay, so you have to put r dash as 0.08% because that's monthly basis. So essentially you always remember whatever is your n, your r also should be in that unit only. Okay. Okay, so put all these values. R dash is 8, so it is nothing but 30,000 into 1.8 power 40 into zero point 0.8 divided by 1.8 power 40 minus 1. Okay. 1 second. There is 1 0 here. Okay, so that's a typo here because 0.09, right? So if I divide, there will be 1 0, so 0.008 will be there. So it will be 0.008, so that will be 0.8% per month. Okay, so here, yeah, this is fine. Here it will be everywhere 1 0 will be there, additional 1 0 will come. Okay, so like this, 00, sorry. Okay, so if you calculate this value, you should get around 880 rupees. So I'm rounding it off because I don't have the exact answer here, but you can do it yourself also. Everything is in front of you. Okay, so like this, you should be able to do this kind of problems. Okay, so let's take one more question. Again, this is a template question, but I'm just giving you some these things. So with interest rate of 9% compounded semi-annually, value of 800 rupees investment after 6 years would be. That is the question. So here, now the thing is, they have given you some R, which is 0.09. Okay, but it is compounded annually. Semi-annually, which means M will be 2, right? Because it's a semi-annual case. And they're asking you after 6 years. So you have to convert everything in year. So you have to convert this R into effective annual rate. So that will be 1 plus R by M minus 1, right? So 1 plus R by M, so that will be 0.045 power 2 minus 1. So you should get 0.09202. Okay. And then they are asking you what is the future value of this 800 investment. So that will be nothing but you have to use this effective interest rate, this value. So that will be 0.0902 power 6, because they are asking about after 6 years. Okay, so this, if you solve this, you should get, okay, let me just do it, because 1.0902 raised to 6 into 800. Yeah, so no, it is 9202. 9202. Yeah, so it will be around 1356.7. Okay, so basically your investment is, almost become, oh, 1 second. 1.7 times, okay, 70% increase in your investment after 6 years. Okay, so like that you should try to solve these kind of problems. Okay, so let me just see if we can take one more. Okay. Yeah, there is one more typical this thing, problem, but we'll take after this one. Sometimes they try to trick students by, asking them to compare which effective interest rate would be greater or lesser, like that. Okay, so we'll look at that. Okay, so before that, let's take one more problem. Okay. Yeah. Okay. So this is the question where, again, you have to be careful about the frequency. Okay, so let's take the question. An annuity of 3,600 is paid at the end of each quarter for 7 years at an interest rate of 8% compounded quarterly. The present value of the cash flow is, this is the question. So here basically they have given you A, which is 3,600. R is given as 8%, so 0.08, right? But it is compounded quarterly. Right? So it will be nothing but 0.08 divided by 4 per quarter, because it's quarter, right? So M is 4, so it is 0.02. So basically in each quarter you get 2%. Okay, why am I converting this into quarters? Because they are asking, because this annuity is paid for each quarter. Okay, and they are asking after, like, this is done for 7 years, so n is nothing but 7 into 4, so 28 quarters. Okay, so basically we are talking everything in terms of quarters. Okay, so now that is the frequency that we are dealing with. Okay, so now based on A we need to find P. Okay, so you have to use this formula. If you remember, this is present worth factor. in your EPS series, equal payments series. So here, if you have access to tables, you should use this table with the effective interest rate of 2% per quarter for 28 quarters, right? But if you don't, then you need to remember the formula, which was 1 uh, 1 minus 1 plus I power minus n divided by I. So this was the formula. So now you need to plug all the values. 3600, 1 minus I is effective, so 0.02. So this will be 1.02 power minus 28 divided by 0.02. Okay. So therefore, if you do the calculations, let me just do it for you. 3600 into 1 minus 1.02 raised to minus 28 divided by 0.02. Okay. So your present value of your cash flow for these many quarters is 766.2.6. No need to put INR because question it's not that. So this is your answer. Okay. So you have to club this class or this week's content with our previous week's content also. Otherwise, these are not. I mean, this is continuation of last time only. It's just that some extra formulas added because of this continuous compounding, and there also everywhere you have to replace I with e power r minus 1. Okay. So that is one thing, and then there is one a typical problem or question that is asked. Let me just check. Yeah. Okay. So something like this. The question will be, in which of the following case, which of the following cases, or okay, in which one of the following case interest received would be highest. Okay, this is a typical question, and you will have some options. Let's say let's say 15% compounded annually. Then second option would be something like 15% compounded daily, and I mean, I can change this 50% also, but I'm not doing it because for the sake of ease of understanding. But the concept remains same. So it could be something like weekly, and something like 15% compounded continuously. Okay, continuously. So basically, what is happening here is, as if you remember, this I or interest is nothing but F minus P, right? So what you can do is basically P, you can assume it as a constant because they have not mentioned anything. So essentially, to have maximum interest for a given P, this ratio should be maximum, right? So basically, F by P should be maximum. F by P should be maximum, And what is f by p? It is nothing but 1 plus r by m power m minus 1, right? Which is nothing but your EAR, right? So you have to go to the starting of the class. This f by p, it has to be maximum, right? So that means this 1 plus r by m power m minus 1 has to be maximum. Okay, so it also means, like, this will be maximum if your effective interest rate is maximum, and that effective interest rate is nothing but given by this formula. Okay, so let's talk about annual, because the largest that they are doing is annual. So other frequencies are more than the annual, but I mean, you understand, right? The largest time period that is given in the options is annual, so effective interest rate is good enough to judge. Okay, so in case 1, if you see R is same. Okay, so basically, I mean, what I'm trying to say is, if you calculate EAR1, it will be nothing but 1 plus here in case 1, m will be, since it's an annual compounding, m is 1, so it will be simply 0.15 power 1 minus 1, so it's nothing but 0.15. Okay, so uh, that is your effective annual rate. Makes sense, right? Because it's compounded annually. Case 2, your m is nothing but daily, so there are 365 days, so your EAR in case 2 would be 1 plus 0.15 divided by 365 power m is nothing but 365 minus 1. Okay, so if you do this, you should get 1 second. Yeah, sorry. 1 plus oh, okay. So 1 plus 0.15 divided by 365 whole raised to 365 minus 1. Okay, so if you do this, you should get 1 second, you should get 0.1618. Okay, so in this case it is higher than the case 1. Okay, so case 3, m would be, since it's a weekly thing, m is 52, so EAR in case 3 would be 1 plus 0.15 divided by 52, 52 minus 1. Okay, so let's do that also. See what do you get. You'll get 0.1616. Okay, and case 3, which is your continuous compounding, so m is nothing but infinity here, so EAR for case 4, we know the formula, it is e power r minus 1, right? So shift E, R is 15%, and then minus 1, so that will be 0.16183. Okay. Okay. Since it is very close to case 2, let me calculate case 2 again. 1 plus 0.15 365 raised to 365 minus 1. Okay, so it was, yeah, it was, if I don't round it off to 4 digits, it is 79. Okay, So by doing this brute force calculations, you understood that this is the case 4 has highest EAR. So therefore F would be maximum for given principal or present value. Therefore the interest would be maximum in this case only. Correct? Okay. But the thing is, there is you know this thing. What do you say? You can do it this way also. One simple trick that you can do is, see, EAR is nothing but, I mean, instead of doing all these calculations, let's say you don't have a calculator available with you, and such questions come in the exam, especially some competitive exam where you don't have enough time also, even if you do have calculator. So the formula is like this, right? R by M power M minus 1. Okay. So for constant R value, okay, so let's assume that rate of interest is constant, some R, and they are varying M. M varying means frequency is varied, which is what we did in the last problem. So this effective annual interest rate is nothing but function of M only, right? Because anyway it is function of two variables, R and M, and if I make R as constant, then it is a function of single variable M. Okay. So one thing you can do is, again, you can calculate the derivative of this function with respect to M. That gives you slope of EAR with respect to M, isn't it? So what I mean by that is, if I take derivative of EAR with respect to M, then this becomes M into 1 plus Rm power M minus 1 into, now inside the bracket we have to go. So 1 is gone, so R by M, so that will be minus R by M square, and minus 1 goes away, so like that. Okay, so basically I'm using chain rule of um, this thing, what is it? Chain rule of differentiation. Okay, so then what do you have? You have minus R by M, gets cancelled, right? So you have 1 plus R by M power M minus 1. Okay, so this is nothing but rate of change of EAR with respect to M, right? We sometimes call it as slope, etc., but it's nothing but rate of change of EAR with respect to M. Okay, so R is constant here. Okay, so and M is always greater than 1, greater than equal to 1. Okay, correct. So what I mean is, this R value, R is a positive, what do you call it? It's not number, it's a positive fraction, let's say, and M is always greater than equal to 1, because it can be annual or quarterly, etc. So it will be always greater than equal to 1. So in that case, R by M is always positive, right? I mean, if you take M equal to 1, then uh, in that case also R by M is positive. Then the thing is, if you look at this d by dAR by dm term, see, I'll write this minus 1 outside so that it is clearly visible. Okay, so you have minus 1 here. R by M is, R by M 1 plus R by M power m minus 1. Okay, so what I am trying to say here is, see, this term is always positive. This term is also always positive only, right? Because if you take m equal to 1 also, it is something power 0, so that will be 1. Okay, in other case, since r by m is positive, 1 plus r by m is also positive, so this thing is positive. But since this minus 1 is there, this whole thing is negative. Okay, so what it means is, this rate of change of EAR with respect to change in m is always negative. Okay, so mathematically it means that, if you increase m, one second, did I do any mistake here? M into this power minus m minus r by m square, mm gets cancelled. Okay. So this thing is negative. Okay. One second. See, the idea is, as m increases, your EAR also increases. You can see right here, case 1 m is 1, case 2, I mean, you can see right, if when m goes to infinity, you are getting maximum EAR. Okay, so I'm trying to prove that mathematically. It's just that um, r by m minus r by m. So slope is negative. That means if m increases, dr should decrease. Hmm. One second. It is, I mean, the final answer is coming opposite to what it should. So that's why I'm checking whether I've done any mistake here. Hmm. One second, I'll just check it again. Plus by m raised to m minus 1. R is a constant, correct? Dy by dm. Okay, one second. Maths look correct only. Let me just see. I think yeah, it will be, yeah, this differentiation is not correct, I feel, because um, this derivative is also there, right? Let me just see what is the final answer. Yeah, I think the mistake is here. This differentiation we did, but it's not that straightforward. No, let me just do it again. Okay, before that, we'll do some substitutions, etc. Okay. Because the result that we are getting is incorrect, so that means there is something mistake. Okay, so here the easy way would be put some u equal to 1 plus r by m. Okay, so that means EAR is nothing but uh, u power m minus 1. Okay, so now if you do this du equal to this, then what should you get? Yeah, I think you should take log on the both sides first. Yeah, because the problem is this is also some function of m, right? And then you have power also some function of m. So it's not like straightforward chain rule here. Yeah, I understood now. The thing is, now you have to take log on both sides. Then maybe it will be, ln u. Actually, we can neglect this one here because it's a positive constant, right? So uh, neglect one since it's positive constant. So now you have to do the differentiation. Yeah, so now, yeah, I think then it's quite difficult to do differentiation. I mean, not that difficult, but the question is with respect to which variable you are doing the integration differentiation. Okay, so this will be 1 by EAR ln of sorry, differentiation of EAR with respect to m. This side it will be like this, and here it will be ln u will be there because we differentiate m once, and then you'll have 1 by u du by dm. And from here, yeah, the differentiation was incorrect actually. That's why this du by dm will be minus r by m square. Yeah. Okay. Yeah, this is correct now. So this is our this thing, right? Quantity of interest. So what it becomes? Ln of u. Let's say 1 plus r by m. Then you have m and 1 by u. So I can write u as m plus r by m, right? So this is m into 1 by u. So that will be m by r plus m, and du by dm is minus r by m square. Correct, right? Yeah, this m square should get cancelled out. Okay. So you basically have EAR into ln 1 plus r by m plus, sorry, there will be minus sign here, minus r by r plus m. So that will be, we want r by m, right? So essentially it is r by r plus m. Okay. So if r by m is our m plus r by m. See, the idea is, what I'm trying to say here is, the whole idea behind doing this integration was, I want to prove that this is always positive. This LHS is always positive. That means as m increases, your EAR will always increase, and to prove that we have to look at the terms on the RHS. Okay, see this EAR is always positive. Okay, so this term is always positive, so there is no question about this. Now the sign of RHS will be decided by these two terms on the uh, inside the square bracket, right? So I want to check, is there any easy way to say that this is always positive? It has to be, because I know the answer, but I'm just trying to see um, what about this term. Okay, see, one thing you can do is you can convert everything in terms of R by M. Okay, so see, because we have this U variable, right? So if I do everything in terms of R by M, so what this bracket becomes is nothing but this will become ln of U minus R by M will be U by U plus 1, correct? And U will be always greater than 1. Okay. As n tends to infinity, it will achieve 1. Okay. So as m tends to infinity, oh no, sorry, this is not correct. This is R by M, so that is 1 minus U. Okay, so R by M is U minus 1, so U minus 1 will be here, and here R by M is U minus 1, U minus 1, plus 1, correct, no? R by M is U minus 1. Oh, so in that case, you just have U here. In that case, you have ln of U minus 1 plus 1 by U. Correct, no? Yeah, now it makes sense, right? Because the thing is, see, ln any natural log is always greater than 1 if U is greater than 1. See, what I'm trying to say is R by M is a positive fraction, right? And as M tends to infinity, R by M tends to 0. And since U is 1 plus R by M, when M tends to infinity, U tends to 1. Okay, so U is always greater than 1. This proves that U is always greater than 1, right? So that means ln of U is always greater than 1. Is it so? No, right? No, you can't say like that. Okay, so we need to plot this and we'll see. Let me just check. There is online plotters, all right? So if I plot this function for values of U greater than 1, what do I get? Y equal to ln of x, let's say, plus 1 divided by x is 1. Y. Okay. Yeah, now it makes sense, because the thing is, if you plot this function, I have just plotted it. You can plot it yourself using Desmos or anything. So you'll see this function. Let's say this is your U and this is your function ln of U plus 1 by U minus 1. Okay, so this is your basically Y value. You'll see it goes like this. Okay, you can also mathematically do this, but we are running out of time. But what I'm trying to say is U equal to 1 is a minima for this function, and for U value is greater than 1, this function is always positive. Okay, So this is your, let's say, 0, and if you want I can use some other color also. So you can check it out yourself. It looks like this. So what it means basically is this D of your EAR with respect to DM is always greater than 0 or always positive. So in that case, the conclusion that I wanted to make, I thought the differentiation is easier, that's why I did that. But as it turns out, it's not the easy differentiation, it's quite lengthy one. And you can take this ln of u minus 1 1 plus 1 by u as a separate function. You can do differentiation, equate it to 0. You'll see that u equal to 1 is the critical point, and if you take the second derivative, that derivative will come positive. So in that case, you have a uh, minima at u equal to 1. Okay. So when you say u equal to 1, that means r by m equals to 0, right? Because u is 1 plus r by m. So that is what I'm trying to say, that you know uh, this thing, as m increases, your EAR will always increase, and the conclusion is therefore maximum EAR will be obtained as m tends to infinity, and that is the case of continuous compounding. Okay. And least will be for or minimum EAR will be obtained for m equal to 1. So basically annual compounding. Okay. So these kind of questions can be asked. They are asking sometimes to calculate values for different m, or sometimes they will ask you to write them in increasing order or decreasing order, anything like that. Okay, so with that, yeah, it's already 8, so we'll stop and see you next class. Hopefully this last part was not that difficult. Actually, I thought it's a easy differentiation, but it's not, because the power is not a constant. So u power m, see, if m is constant, then I can do that usual thing. But here m is also function of, I mean, u is function of m and m is also function of m. So you have to use the logarithmic rule of chain rule of logarithmic differentiation. Okay. Anyway, so with that, we'll stop here and see you next time. Okay. So bye. Good night.